Hi class, welcome to the next section. Today we're going to talk about polynomials. Polynomials are very important, and they're actually one of the easiest things for us to deal with when it comes to calculus, right? So if these used to be like your most contrived function, you're like, oh, I hate dealing with polynomials. They're actually super nice when it comes to applications of calculus, okay? I actually talk about polynomials quite a bit in this course. And again, they're the nicest functions that we get to work with. That being said, I do want to spend quite a bit of time really going over the basics of polynomials, not just the basics, but to an advanced level, obviously. But really understanding how polynomials work is going to help us a lot through this course. So I think this video might be quite a bit longer, probably as long as the first video. I think the first video was around like 40 minutes. So it's probably somewhere around that. In length, we're going to go over some really important topics. Again, if you want a deeper dive into polynomials, then check out my pre-calculus material on that. In this section, chapter 1 is still a review. So we are just kind of glazing over a lot of stuff. So I apologize if some of this is like, oh, I would really want to, explore this topic further. Professor Williams, you should have had some more examples on this kind of stuff. I do apologize, but I do have like complete chapters dedicated to polynomials, complete chapters dedicated to the rates of change and things of that nature. So all the things we're covering in chapter 1, we're really just kind of going over basically, right? Just kind of reviewing. So that's why you're not seeing a lot of like super in-depth stuff in these chapters at first, and hopefully later on it's to a greater degree in the actual calculus material to satisfy some of your curiosities for that, right? But again, my thought process on this was all of this stuff is review, so that's basically what we're doing is reviewing, okay? For those of you who are actually taking my class, you will have quite a bit of practice in your homework sets for this. Since this is OER material at this point, meaning that my course reader that goes along with these videos, and these videos are all open access to the public, I think I'm going to actually make my homework sets open access as well, so that anyone who's watching these videos can have some problems to practice on, okay? So I'll let you guys know if that's the case later on, right? For those of you who are not in my class who are watching these videos. So let's go ahead and stop lollygagging and talk about polynomials, okay? So a polynomial is a function that has the form of a coefficient times our variable to a power, another coefficient times a variable to a power of 1 degree less, and so forth until we get to an x squared power, a linear term, and then a constant term. Now, if one of these coefficients is 0, then obviously that term will be missing, right? So each collection of these things that we're adding together is called a term. So this is one term, this is its coefficient, and then this is that power form that is applied, where that coefficient is applied to, okay? So all of these things are important. They play different roles. Really, the most important parts are the first term and the last term, right? So we generally write this in descending order of power. So highest power first. The power is the degree of the polynomial, and then we move downwards, okay? Sometimes you'll see it written the other way, so that the constant term is first, and then it increases in ascending order to the highest degree, which is fine as well, right? It doesn't really matter what order we put things in, but we typically like to have the powers go in order, okay? So one of the most important things that we like to talk about is the degree of the polynomial n, okay? The highest power that's present. So the degree of the polynomial does a lot of stuff for us, which we'll go over in this video. Again, this is a review video, right? So the degree of the polynomial kind of tells us what the general shape of the polynomial takes when we graph it, right? You can think about it as the degree of the polynomial tells us what the end behavior is, right? What happens at the extremes when I tend to go towards infinity or negative infinity, right? So when I plug in very large values or very large negative values, what does my polynomial tend to do? The degree of the polynomial also tells me how many zeros I have, okay? So every polynomial has n zeros, right? They don't all have to be real. They can be complex as well. but every polynomial has n zeros. That is, I'm skipping ahead a little bit, but that's what is called the fundamental theorem of algebra. Okay, so later on in this class, we talk about the fundamental theorem of calculus, right? Which is actually the name of the last chapter of this course that we're doing for Calculus 1. But the fundamental theorem of algebra we'll go over in more detail when we get there. Okay, so n is the degree of the polynomial. It does lots of important things for us, right? It talks about n behavior, talks about the general shape of the graph and how many zeros we have. A to the n is the lead coefficient. It's the coefficient that is attached to the highest degree term. The lead coefficient really just kind of tells us what the polynomial looks like overall. Basically, is it concave up or concave down? That's a little bit loose terminology there because a high degree polynomial can have several concavities present. So it really just kind of tells us the general shape. Is it, I guess for lack of a better word, is it right side up or is it right side down, right? Those two things together with that variable term of x is the leading term, right? Each of these is a term. This is the leading term. A naught is the constant term. It does not have any variable part. Its variable part actually is x to the 0 power, right? So it goes n minus 1, n minus 2, n minus 3, all the way to our square, our first power, and our 0 power, which we should know at this point, x to the 0 is just 1, so we don't have to write it, right? So a naught is the constant term. It has no variable part. It's just multiplied times 1. Okay. Each a sub I is a coefficient. So an is a coefficient. An minus 1 is a coefficient. A2 is a coefficient. Another thing, notice that the subscript on the coefficient matches its power. Okay, that's typically how we tend to write these. It just keeps things easy to work with. Okay. Each a sub I, x to the I power, is a term, as I stated before. Okay. So now let's talk about what the effect of the degree has on our polynomial. So I anecdotally talked about this just a second ago when this first slide for n is the degree of the polynomial came up. So I'll talk about it in a little bit greater depth right now. Okay, so again, when we're analyzing polynomials, there's numerous things that we got to take into consideration. First thing is the degree of the polynomial. It tells us a lot about what's going on. Okay, the lead coefficient along with the degree, so really just this lead term is really what's most important to us, right? We want to know about the zeros, the x-intercepts and the y-intercepts, so both zeros, right? That's pretty much it. Okay, so let's talk about the degree first. The degree of our polynomial is going to tell us what the general shape is, right? So it kind of follows a pattern. So not only does it tell us the general shape, but it tells us the max number of zeros and the actual number of zeros when we take into consideration the complex zeros as well. Okay, so if I have a polynomial of degree 1, maximum I have 1 0. Okay, I will always have 1 0. Okay, when I have a quadratic, I have a maximum number of 2 real zeros. If this is moved around so it doesn't pass through the x-axis, then I still have 2 zeros, but they're 2 complex zeros. Okay, if I am just touching the x-axis, right, not crossing it, but have one point in common, then I have 1 0, but it is a multiplicity of 2, so there is actually still 2 zeros, right? So the degree tells me the number of zeros that I have, as well as the generalized shape, right? So notice that this is a first degree. It starts from the negative direction and it ends in the positive direction. When it is a squared term, it starts from the positive and it ends in the positive. 3 starts from the negative, goes to the positive. 4 goes from positive to positive, negative to positive, positive to positive. You see that there's sort of a pattern going on here, right? All of the odd power polynomials are very linear in shape, right? Okay, so it's not linear, but it basically does what a line does, right? It starts at the bottom, it goes to the top, and depending on the degree, tells us how many zeros are in between those end behaviors of it, right? So starting from the negative direction and the ending in positive. When it's an even degree, it's always basically U-shaped, right? This is basically a U with some squiggles in the middle. The squiggles are determined by the number of zeros that are present, okay? So the degree of a polynomial tells us what the end behavior is, okay, what happens at infinity, and it tells us the number of zeros present for the polynomial, right? Okay, so that's just me repeating. So zeros are very, very, very important, right? In pre-calculus, spend a lot of time really developing methods for finding the zeros, okay? Generally, we try to focus on the real zeros if possible. The rational zeros really is what helps us the most, but we spend a lot of time with that, okay? So multiplicities of a zero are very important as well. It helps us to kind of determine what it is that a graph does, right? So if a polynomial has a zero with multiplicity, and that multiplicity is an odd number, okay? So meaning, let's say x equals 1 is a zero, and there's 3 of them, right? 1, 1, 1. So it's a repeated 0 3 times. Then what happens is, at that value of 1, my graph passes through the x-axis at 1. If it's an even multiplicity, it bounces off of the axis, right? So we're going to say that lambda is a 0, okay? So p of lambda is 0. If I plug lambda into my polynomial, I get 0 out. Let's say it has a multiplicity, and that value of multiplicity is m. So it's repeated m times. It can be repeated twice, 10 times, 30 times, 27 times. It doesn't really matter, but m is the number of times it's repeated, okay? So I have a factor of x minus lambda m times, so this is what that factor would look like, x minus lambda to the nth power, right? So if the multiplicity value is odd, so if m is, so there's only one of these, or 3 of these, or 5 of these, or 7, or 9, or 11, or what have you, then I'm going to cross the x-axis at that point. If my multiplicity is even, then I'm going to bounce off the axis at that point. So if I'm coming from the bottom, when I hit the x-axis at that location, I will turn around and go back negative. If I'm coming from up top above the x-axis, as I reach this point, when I hit this on the axis, I will bounce off of it and go back in the positive direction. Okay, so even multiplicity means you bounce off of the axis. Odd multiplicity means you cross the axis, right? So this here would be an example of an odd multiplicity. It crosses. So that means that this is a 0 either once, or 3 times, or 5 times, or 7, or 9, or 11, or some odd number is the number of repetitions. Here, this is an even multiplicity. So this 0 shows up twice, or 4 times, or 6 times, or 8, or 10, or 12, or what have you, right? So, for instance, if this was a, let's say, a 27th degree polynomial, well, this would show up an odd number of times, and this should show up an even number of times. But there would be only 2 distinct zeros. One that shows up in odd number, and one that shows up in even number, okay? So, depending on how many times this one shows up or this one shows up will determine what the power, the degree of the polynomial is. Okay, so now let's talk about factoring, right? Because zeros are important. If I know how many zeros or the multiplicities of them, I can get a better idea of what my graph looks like, right? So let's talk about the complete factorization zero. So if a polynomial has a degree that's 1 or larger, right, then there is going to exist an a, which is that lead coefficient, a lambda 1, a lambda 2, so forth, that are complex. Okay, so these can be complex values. My first term cannot be 0, okay, such that I can factor my polynomial to be a times x minus lambda 1, x minus lambda 2, and so forth and so forth. So we saw this already in the example I had in the previous section, in the last video that we did for rates of change. Okay, I used this form to find the formula for the guy throwing the rock off a cliff, right? So then that leads us to the zeros theorem. right? Basically, if I can factor these, then these are all zeros, right? All of these are my zeros. So if I have a polynomial that's a degree of 1 or higher, then I'm going to have exactly n zeros over the field of complex numbers. So, like I said before, any polynomial of degree n has n zeros, right? Taking into consideration multiplicities and taking into consideration complex zeros as well, I will have n zeros, right? So counting any multiples and counting my complex. This brings us to the conjugate zeros theorem. This is basically just saying if I have a single complex zero, then its complex conjugate is also a zero, right? So any complex zeros also come in pairs, and this is true only if all of my coefficients are real numbers. If I have a coefficient that is imaginary or complex, then it is possible that one of my zeros is complex and it does not contain its complex conjugate, right? So if all of my coefficients are real and I have a complex zero, then its complex conjugate is also a zero for my polynomial. Okay. So if this is a zero, then so is this, if all of my coefficients are real numbers. So real numbers means radicals, fractions, pi, e, anything except for something with an I term in it. Okay. Radical zeros theorem, very, very similar to the complex conjugate zeros theorem, which is that if I have a radical zero, it also has its conjugate as a zero, as long as all of my coefficients are rationals, right? So either whole numbers or fractions, not radicals. Radicals are irrational numbers. So if all of my coefficients are whole numbers or fractions, okay, and one of my zeros has a radical in it, then the conjugate of that radical, the radical conjugate, is also a zero, right? So basically, if I have a plus b square root c as is a zero, then so is a minus b square root c. And again, that's only if all of my coefficients are whole numbers or fractions. If I have a radical as a coefficient, it's possible that the conjugate is not a zero. Okay. So if any a sub I is a radical, then it's possible that a radical zero does not have its conjugate as a zero, as I said before. So then that brings us to the rational zeros theorem. I'm just saying, like, let's say that I have these, okay? If all of these are rational, just like before, so whole numbers or fractions, okay? And my lead term is non-zero, and my last term is non-zero, then each of these coefficients are integers, okay? So not fractions, this doesn't count for fractions. So they all have to be integers. Then all of my zeros that are rational come in the form of lambda a naught over lambda am. Lambda a naught are all the possible factors of this constant term, and lambda an are all the possible factors of this first term. So all of my zeros that can be whole numbers or fractions are based on the lead term and the constant term. Okay, so again, lambda subscript a naught are all the possible factors of a0. So let's say that this was 10. All my options would be 10, 5, 2, and 1, taking the plus and minus terms into consideration. Lambda a sub n is all the possible integer factors of the lead coefficient, right? So this is a very, very powerful theorem. This combined with the radical zeros theorem and this conjugate zeros theorem, you should really be able to factor almost anything, okay? Pretty much anything that we have in this class, you should be able to factor. We use these theorems with synthetic division, okay? So at my campus, not a lot of people teach synthetic division, but I find it's super, super helpful. It's very, very strong. Not only does it allow us to factor really, really quickly, actually, but it also allows us to evaluate a polynomial very, very quickly. So I use it for many, many things. I think it's a very important tool that's very, very useful, and I stress it quite a bit to my students. So if you haven't seen it before, we are going to do a couple of examples. Again, I have whole videos on synthetic division where we do tons and tons of examples. All these polynomial things I have in the pre-calculus section with lots and lots of examples. So if you want to go a little bit further into some of these things, you can refer back to that video series or that course reader, which is also available on my website. So, you know, I hate to refer you somewhere when we're already in space talking about stuff, but I mean, I don't want to do the same thing over a million times, right? So, there are places for you guys to find some of these resources that I provide for you. So, let's see. So the only thing we can't do with these two theorems together are the radical zeros and complex zeros. So synthetic division really just helps us to find the rational zeros. So what we do with synthetic division and this rational zeros theorem is we find all of the whole number zeros and all of the fractional zeros, right? Like 1/2 or 3/2, things like that. All we factor it down as much as possible. And ideally what should be left is something that is maybe non-factorable over the integers. So then we just use the quadratic formula. And then we get our two radical zeros or we get our two complex zeros, right? So the goal is really to whittle it down to something that we can then solve using quadratic formula or whatever other method that we know, right? So, okay, there we go, just like I said before. So use these two theorems, allow us to factor a polynomial down to the point that we can identify its non-rational zero. So basically, work this thing down, factor as much as possible. We get it to a point where we can just throw the quadratic formula at it. So let's go ahead and do an example. So we're going to factor a very large polynomial, and we'll use synthetic division to do so. And if we come to a point where synthetic division stops, then we will use the quadratic formula and finish factoring out our problem. Okay. So here we want to factor out this 5th degree polynomial. So what we're going to do to start is find out all the possible rational zeros. So I'm going to use that rational zeros theorem and identify any possible whole numbers that could be a zero, right? And any fractions that could be a possible zero. So what I'm going to do is I'm going to take all the factors, all the integer factors of 4 and put them in a numerator position, and all the possible factors of 2 and put them in a denominator position, and I'm going to write all the combinations of numbers that pop out with that. Now when I do this, I'm using the plus and minus of these factors and the plus and minus form of these factors. So 4, I know, breaks down to integer factors of 4, 2, and 1. 2 just breaks down to 2 and 1. Okay, so the factors of 4 are 4, 2, and 1. And the factors of 2 are 2 and 1. Okay, so then we put these things together. Again, we use all the positive and negative values and all the combinations of those. So my possible zeros, okay, which are the factors of the constant term divided by the possible factors of the lead term, are as follows, right? So we're using plus and minus because I can have two negatives that multiply to a positive. So I have to take the negatives into consideration, especially if I have negative signs mixed into my my polynomial. There's another theorem that says the number of sign changes will tell you how many positive and negative zeros you have, right? Which I never use, so we're not going to really get into it. It's not super, it's useful, but it's not super necessary, right? So it's very possible, it's not possible, I have some negative zeros in here. So I'm going to use the plus and minuses, right? We always do. And what I'm going to do is I'm going to build all combinations. And really when I do this, I start with the first one and I just go in order in the bottom. So for instance, I have 4 and 2 is 2, right? So I have plus and minus 2 as a possible zero. I also have 4 over 1, which is 4. So plus and minus 2, plus and minus 4. Next I have 2, so I go 2 over 2, which is 1, and 2 over 1, which is 2. So I have 4, 2, and 1. Notice that 2 over 1 is 2, but so is 4 over 2. So that doesn't mean that it's more likely to happen because I have two different things that happen to make it a 2. It's just how it goes. So anytime I have a possible zero that repeats, I I just write it once, right? So my possible combinations then are 4 over 2, which is 2. I have 4 over 1, which is 4. I then get 2 over 2, then 2 over 1, then 1 over 2, and 1 over 1. Okay, but if I put these in order, right, disregarding any repeats, 4 over 1 is the largest, so 4. Then I have 2, which is either from this one or from this one. It doesn't matter. They're both the same value, so I only have to write it once. Then I have 1, okay, plus or minus 1. And then the smallest is plus or minus 1/2. So I have 4 possible zeros, which actually is 8 possible zeros, because I have to take in the negatives for consideration as well, right? So these are the possibilities for my rational zeros. So you see we have whole numbers and then one set of fractions that's possible. Generally when I do this, I start with plus or minus 1. I'll either choose plus 1 or choose minus 1 to start. So those are always the easiest. And then I'll move up through the positive numbers, or not through the positive numbers, I'm sorry, through the whole numbers. And then I'll go to the fractions if necessary, because the whole numbers are way easier to use with synthetic division. Okay, so the way that we set up the synthetic division is that we take whatever zero it is that we're looking at, right? So again, I like to start with either the positive one or the negative one. And then we write the coefficients of our polynomial. So I only need the coefficients, the 2, 7, 2, negative 11, negative 4, and 1 and 4. I'm sorry. I don't need the power terms associated with it. I don't need the x to the 5th, the x to the 4th, etc., etc. Just the coefficients and their sign. If something is missing, like for instance, if there was no x cubed term, I would use a 0 for a placeholder. So don't just get caught up and write only the coefficients. If something's missing, keep a 0 there, right? Otherwise, your whole thing will be messed up. So I have 8 possible rational zeros. Our polynomial is of degree 5, so I should get 5 separate zeros. Maybe not separate, but I should get 5 zeros out of this. Okay, some of them could be repeated, which is fine. It's okay to have multiplicity. So remember that if I plug in one of these zeros, one of these values, I get out 0, then that means that my factor looks like x minus whatever that number was, right? As I said before, the easiest to use is either 1 or negative 1. So let's go ahead and set this up. So I have 1. I'm using x equals 1, which means that x minus 1 will be a factor if this works out. Okay. I'm using 2, 7, 2, negative 11, negative 4, and 4. Right? 2, 7, 2, negative 11, negative 4, 4. The way that we start this off is I'm going to add these numbers. I always start with a 0. I will add these numbers together and I'll get my 2. Okay. I take this 2, I multiply it times 1, and whatever I get, I put in the next slot, which is 2. So now I add these together, I get 9. Multiply 9 times 1, that goes here, and I get 9. 2 plus 9 is 11. Multiply and put here. Add those, I get a 0. Multiply is a 0. Add those is negative 4. Multiply those is negative 4. Add those, I get out 0. So it's really fast, really easy. Okay, I went as slow as I could for you guys, but generally you can do this really quickly. So again, I start with a 0. I add, that's 2. Multiply is 2. Add is 9. Multiply is another 9. Add is 11. Multiply is 11. Add is 0. 0. Add. Multiply. Add. Okay, so I typically can do this as fast as I can write it. If I get a 0 out for the last entry here, that means that this is a 0 to my polynomial. Okay, so that means that x minus 1 is a factor, right? I put a circle around it. That means I'm good. Now what happens is, what's left here, this 2, 9, 11, 0, negative 4, that is the polynomial I get out when I divide my first polynomial by x minus 1. Okay, so if I took x minus 1 times 2x to the 4th, 9x cubed, 11x squared minus 4, I would get out my original polynomial, right? So I found a 0, and not only did I find my 0, but I also got out what I would if I were to have divided it by that binomial term x minus 1. So it allows me to factor, and then it gives me out the remainder, which I then need to factor to continue on with my factorization. So I found one factor, so now this is what I'm going to try to factor to find my next set of factors. So I'm going to use the same one I just used. I really use the same one. If it works, I use it until it doesn't work anymore. So x equals 1 worked, so I'm going to use x equals 1 one more time, right? So x equals 1 is a 0. That means that x minus 1 is a factor, which means that if I took my original polynomial divided by x minus 1, I would get out this, right? Starts with a constant, then the x, then the x squared, then the x cubed, then the x4. Or if you're going the other way, just know that I took a 5th degree polynomial, I divided by a 1 degree polynomial, so I will get out a 4th degree polynomial. So that first term is a 4th degree, third, squared, constant, x, and then constant, okay? I generally go in this direction when I do it, and I say, oh, constant, and then x squared, x cubed, x4. That way, I know I'm doing it right, okay? So now, since this worked, I'm going to, so if I rewrote this, my original polynomial is x minus 1, the factor I just used, times what I just got out, okay? So now I need to finish factoring this in order to continue factoring this, right? Because I already found one factor. So again, I'm going to use x equals 1 one more time, right? So in order to continue our resulting quotient polynomial from the synthetic division, we're going to use this again because it could have multiplicity, right? So this is what I had before. Okay, I didn't just do it all again. It's the same one. I'm going to start from where I left off. Okay, I'm going to use x equals 1 again. I'm going to kick it off with a 0. 2 plus 0 is 2. Multiply is another 2. Add that and I'll have 11. Multiply that and I get 11. Add that is 22. Multiply is 22. Add is 22. You see, I'm getting larger and larger and larger. I'm not getting towards -4. So it does not work. Okay, I did not get a 0 out. X minus 1 is a multiplicity 1. It's only a 0 once. It does not work a second time. Okay, so it's a 0 of multiplicity 1. It's not a double 0 or triple 0 or whatever. So what I'm going to do is I'm going to move on to the next possible 0. Again, I always use +1 or -1. I've already used +1. -1 is the next easiest one. I'm going to use that with this polynomial, right? This 2x4, 9x cubed, 11x squared minus 4. Because I've already whittled it down. I'm not going to start all the way over from my original. I'm going to go with the point where I'm at. So I'm going to go ahead and do this again, but I'll use -1 instead. Okay, so 2, 9, 11, and -4. Right, so we'll try x equals -1. 2, 9, 11, -4. Okay, so I'm going to start over again with just this one. So this is, again, me just cutting and pasting, putting our original work. Instead of using 1 like I did before here, I'm going to use -1. So I'll start off with the 0. I get 2. Multiply is -2. Add is going to be 7. -7. 4. -4. And then a -4 again. Multiply those will give me a +4. Those together will give me a 0. Okay, so I got another 0. So I found one of my zeros, one of my factors, and another one of my factors. I'm going to go ahead and try it again. Okay, so here I now have a constant x, x squared, x cubed. I'm now down to a cubic. Okay, so let's go ahead and try -1 one more time. Let's see what we get. So I'm going to use 0, 2, -2 will go here. That'll give me a 5, -5, -1, +1. That's not going to be 0. Okay, so I have one factor, two factors. This is not, neither of those have a multiplicity. Okay, but I've whittled my way down to a cubic factor. So let's go ahead and try our next 0, which is +2, right? I could use +2 or -2. We'll go ahead and use +2. So this is where I left off last time, right? This was the last time that it worked. That's the last result that I had was here. Oops. the last time that it worked. So this is what I'm going to use. I'm going to go from this point. So I'm using x equals 2. Okay. If I add those together, I get 2. Multiply those, I get 4. Then 11. And then 13. As you can see, I'm getting very, very large. I'm going to add something and then make it larger. I'm not getting towards -4, right? So 2 doesn't work. So I'll take that same result, 2, 7, 4, -4. Let's try -2. Okay. So again, I'm going to start with 0. Add those together. -4. That'll give me 3. -6. -2. Gives me +4. And I'm good. Okay. So I have zeros of 1, -1, and -2. I can try this again, or I can notice that I'm down to 3 terms, which means constant x squared, right? This is now a quadratic. I can continue to use my synthetic division. I can try this again. 0 of -2. If it doesn't work, I can move to 4, which isn't going to work because just looking at what's left over, my possible zeros are going to be positive -2 and positive -1/2, just from using the possible zeros theorem. And what's left over, right? I have a 2 and a 2. So combinations of factors of 2, combinations of factors of 2, numerator and denominator. Easiest is just to apply either a factoring method or like a standard factoring method or quadratic formula at this point. Okay. So at this point, I'm just going to go and work with it from what I have, right? So I know plus or minus 4 is no longer an option because of the possible remaining zeros from the form that I have. So what I have so far is that this is now factored down to a 0 of -1, a 0 of +1, a 0 of -1, and a 0 of -2, and then this quadratic. So I really just got to finish factoring this, and I have everything. So it's possible that this is 2 complex zeros. It's possible that this is 2 radical zeros, or it could be that this is now has a real zeros, right? Maybe it's a whole number, maybe they're fractions, I don't know. So let's just go ahead and try a factoring method that we have. I use what's called Professor Choi's, my office mate. She showed me this method and I've used it ever since. Okay, so basically the way that this works is you take the factors of the numerator, you take the factors of not the numerator, sorry, the leading term and the constant term, and you just write them below, right? So for 2, we have 1 times 2 and 1 times 2. So we go 2 and 1, 2 and 1. Then what we do is we multiply across. Okay, so I get 4. Here I multiply across, I get 1. And my goal is to see whether or not I can get these to add or subtract to be the number in the middle, which I can, right? I can if 4 is positive and 1 is negative. So since I need the 1 to be negative, this is the value that will be negative. Okay. And since that works out, these two align together and these two align together, this being my x terms and this being my constant terms. So I got 2x minus 1 as a factor and x plus 2 as the other factor. Okay, 2x minus 1 from these two and x plus 2 from this one, right? If you know other methods that you want to use, then use those, right? I see lots of different things in my courses, so this is just one that I like when I get to quadratics that's, you know, factorable, that has a leading term that's non-monic, right? That's not a 1. So that means I can factor this all the way down to this. So I do have a multiplicity for one of my zeros. Okay, so -2 is a multiplicity of 2. So for our last example, let's say we put this all together, and instead of factoring something, let's find a polynomial, right? So let's say I want to find a polynomial that has a 6th degree in standard form, that has rational coefficients, so all the zeros are, all the coefficients are whole numbers or fractions. And let's say that one of the zeros is this radical zero, this complex zero, and x equals 2. And x equals 2 has a multiplicity of 2. So far that's 1, 2, 3, 4 zeros. And since it's specifying me to have rational coefficients, that means that I have to have the conjugates of this radical and the complex conjugate of this complex zero, right? So I know that my factored form looks like x minus 2 squared, because it's got a multiplicity of 2, x minus the first 0 gives me, and also its conjugate, okay, because radicals come in pairs when I have rational coefficients, and my complex 0, which also comes in pairs when I have rational coefficients. So this is the factored form of my polynomial. This is not standard form, it's factored form. The standard form is the form I showed you at the very beginning, where you're basically adding all your terms together. You can see all of your coefficients, etc., etc. So basically what I'm going to do is I'm just going to multiply everything. I'm going to multiply these together and get a polynomial. I'll multiply these together and get a polynomial. I'll multiply that out and get a polynomial. I'm just going to multiply everything together, right? So it's just a lot of arithmetic really at this point, okay? So if I multiply this out, it's just a perfect square polynomial. That's really easy. X squared minus 4x plus 4. Here, if I multiply this out, I'm just going to distribute everything, right? So I'm going to have x squared. Then I'll have x times this term. Okay. So 1 times x plus 1/4. And again, this is going to come from, if you notice that these are complex conjugates for these zeros here. Okay. So really what's going to happen here is I'm really just going to multiply these two together with difference of squares, right? So I got 1/4, and then I'll have minus 3 times 3 is 9/4 times another 2. Okay. This 1x here, this comes from me having x times this whole thing minus x times this whole thing. So I have two negatives. So what happens is that this 3/2 square root basically cancels out. And then I have a negative 1/2, right? This x and this negative 1/2. And then I have this negative 1/2 and this x that add together to be 1 whole x. So it's really, really straightforward. It's nice if you can see the pattern there. That makes it really, really easy, right? This next one will be the same thing. I'll have an x squared term first. Okay. I'll have x times this whole thing and x times this whole thing, right? So I have x times a negative 1, x times a negative 1, and then I will have a negative I root 2 and a positive I root 2. So those two will cancel. So for this next one, I'll have a negative 2x, okay? And then for this last term, I'm multiplying these two together, so that's just a difference of square. So that'll be a 1 minus I squared, so that's plus 2. So then this should be plus 3. 2i squared, which will end up being 3. Okay, so that makes it pretty easy when you see that the patterns that develop out of this, right? That's part of what we want to do in calculus. So I'll just simplify these terms, right? So this will be my negative x. This turns into 17/4. This will be x squared plus 2x plus 3. So now I just want to start multiplying these things together. Easiest one to multiply together first will probably be these last two, and then leave this x squared minus x minus 17/4 at the end because it's got fractions, and I would prefer to keep fractions out of it till the last minute if I can. So I'll pull that one to the side. I'll multiply these two together. Okay, so I got x squared times this whole term minus 4x times this whole thing and 4 times this whole thing, which I can then distribute each term appropriately. Okay, so I got x squared minus x minus 17/4. This is what happens when I distribute x squared. This is what I'll get when I distribute the negative 4x. And this is what I'll get when I distribute the 4. Okay, I'll combine all of my like terms that I have in here. So this is only x fourth. I got 2 cubes. I got 1, 2, 3 squares. And I got 2 x's and then my constant. Okay. And then from here, I'll just do the same thing. And I will distribute across this x squared minus x minus 17/4. Okay, so same thing, x squared times this polynomial, negative x times that same polynomial, negative 17/4 across that polynomial, distribute everything. So that's me bumping everything up by an x squared, me bumping everything up by an x and changing the sign. Okay, so that's a negative, that'll be plus, that'll be minus, that'll be plus, and so forth, and the degrees go up by 1. And then here I'll multiply everything by 17 over 4 and change the sign. And then combine all of my like terms to get my final polynomial, right? So therefore, this is the polynomial that has these zeros. It's a 6th degree. And if I were to go back and factor it, it would be easy to get the 2's, but it would be really hard to find the radical and the complex, because I basically would have a 4th degree polynomial that I couldn't whittle down anymore because it would be non-factorable over the integers. So when we get to things like that, those get difficult, but you won't see any of those in this class. Okay, so that's our discussion on polynomials. Again, there's a lot to unpack here, but the more comfortable you are with polynomials, the easier time you're going to have later on.